Okay, the next one is about a new tool. It's OfP4, a P4 front end for OpenVSwitch, and the speaker is Pfaff.
Hi, today I'm talking about OfP4. That's a project I'm building to be a fast P4 software switch. I'm prototyping it with colleagues in the research group at VMware. It uses OpenVSwitch for packet processing. Let's jump right in. So, what is P4? P4 is a programming language for switches. That means it has some things in common with OpenFlow, and the big one is flow tables, since P4 and OpenFlow both use flow tables pretty heavily. But there are tons of differences too. P4 is much more hardware-centric because it's designed so that you can access specific features of particular hardware. It's a compiled language. You write a program in P4, which might use include files and libraries, and then you run it through the P4 compiler, P4C, which transforms it into a version that's suited for the particular hardware you're using. Flow tables in P4 all have specific types, rather than being homogeneous like in OpenFlow, or at least in OVS. P4 is a real language. It has control flow constructs like if and switch, although there's a lot it doesn't have too, like loops and floating point. It also has arithmetic, which OpenFlow really does not. And finally, a couple of other points. P4 is still being developed by p4.org, which is part of the Open Networking Foundation, and you can join it yourself and be part of the working groups helping it evolve. P4 is increasingly available in hardware, whereas it's harder and harder to get OpenFlow in hardware. Finally, there's a small distinction in that OpenFlow is a network protocol, whereas P4 is a language without a protocol. You can attach whatever protocol you want to control P4 switch. The standardized protocol is P4 runtime, which works over gRPC. There are a few P4 software switches already, so why build a new one? Let's look at the options. There's BMV2. BMV2 is a P4 simulator. It's accurate, but it's not fast, and that's not the goal. We want a fast switch. The academic Tapa switch is fast, but I had a lot of trouble installing it outside of one exact distribution of Ubuntu. The Pisces switch is unmaintained, and it doesn't support P4 runtime, which is what I want to use. Finally, I've seen folks from Intel working on a P4 implementation for OVS. My impression is that this has a hardware focus. That is, it's mainly for letting OVS control P4 capable hardware. I'm interested in a P4 implementation for software instead. I'm also not sure of the timeline or the goals. There's a few other P4 implementations in the works. I don't know much about these, but I don't think they suit my goals either. So that's what led us at VMware to do some experiments toward a P4 implementation using OVS. So now I've explained why we came to build our own switch, which we call OfP4. We didn't want to build a whole data plane of our own and implement all that again. I mean, I'd done that before in OVS. So instead, we decided to use OpenVSwitch. That takes some explanation, and that's what this talk is. This is how the system works. So first, we take a controller that uses P4 runtime and a P4 program that it expects to control. Then we compile the P4 program with a compiler backend that we wrote for OfP4. We take that compiler's output and we plug it into OfP4, and then we connect it to the controller using P4 runtime. Finally, we connect OfP4 to OpenVSwitch. OfP4 then translates P4 and P4 runtime into OpenFlow and uses it to control OpenVSwitch. The overall effect is that OpenVSwitch then implements the P4 program. This uses regular, unmodified OpenVSwitch, since OfP4 is just a daemon process. It does need OpenVSwitch extensions to OpenFlow. That means it won't work with other OpenFlow implementations. So one of the things that we need to figure out for designing a P4 implementation that works on top of OpenFlow is we need to match up the OpenFlow and P4 architectures. The OpenFlow architecture, as implemented in OVS, is a single pipeline. The pipeline can have several tables, and each of those tables can have any number of flows that have a ternary match, actions, and a priority. P4, on the other hand, is really flexible, and you can design a P4 switch to have pretty much any reasonable architecture you want. The one that we thought about as a model for OfP4 is PSA, Standardized Portable Switch Architecture. this architecture has two pipelines, and each of those pipelines has a programmable parser and deparser, and they're separated by a buffering and replication engine. We need to come up with a common architecture between these. So the first thing we did was to delete the programmable parser and deparser blocks. OVS doesn't have a programmable parser or deparser, so we have to make do with what OVS has and use the headers and protocols that OVS supports. So as you can see, there's still a difference between the architectures. OVS doesn't have two pipelines, and it doesn't have a packet buffering and replication engine. So one argument would be that we could have removed them to make the architectures just alike. But OVS is flexible enough that OfP4 can make one pipeline look like two, and we can implement that replication engine ourselves in OpenFlow. So we decided to keep the two pipeline model. We're hoping that this makes it easier to adapt P4 programs to work with the OfP4 architecture. So we've got an architecture figured out, and now we've got a lot of details to figure out. This slide shows a skeleton of how you might write a parser in P4 for a program that cares about Ethernet and IPv4 headers. On the left, you see a bunch of data declarations that express the structure of Ethernet and the structure of IPv4. And on the right, you can see P4 code that says how to extract those headers from a packet. For a normal P4 architecture, you compile this as part of your program, and it would define how the switch functions at runtime. With OfP4, we have to do it differently, since there's no programmable parser. Instead, the OfP4 architecture looks more like this. Take a look at what changed. We X'd out the parser code because the programmer doesn't define in OVS how parsing works. Instead, OVS does that with its fixed parser. We still have the headers, but only the fields that OVS knows how to match on are left. This isn't an exact representation of what OfP4 offers on this slide, because OVS pre-processes some of the fields, like the fragment offset, for example, but it should still give you a good idea of what's there and what's gone. And the headers aren't programmer defined anymore. Instead, they're part of the P4 architecture that OfP4 offers. That is, you don't write them in your P4 program. You just include the architecture include file, and it defines these for you. So that's fields, what you find in actual packets. Let's talk now about metadata. So metadata. Both OpenVSwitch and P4 have a couple kinds of per packet metadata. They both have what P4 calls standard metadata, which is information about a packet that isn't included in the packet itself. That's things like where the packet came from and where it should go next. Both of them also have what in P4 is called program metadata, which is like local variables for processing a particular packet. In P4, the programmer can define whatever program metadata it wants, and in OVS, the programmer gets a bunch of numbered registers. With OfP4, we can keep a lot of the P4 standard metadata because it corresponds to metadata that OVS also supplies. That's things like the input port, the output port, and the priority. But we have to get rid of other metadata that OVS doesn't support, like all of the P4 metadata related to timestamps and queue lengths. OVS just doesn't support any of that. OVS doesn't support named metadata either, but OfP4 can make that work. Let's see how. Let's see how everything matches up. We start with some P4 standard metadata and program metadata on one hand, on the left, and with OVS fixed metadata on the other, on the right. So first of all, OVS matches up the standard metadata in a predictable way like this, where the input port matches the input port and so on. Now, for the program metadata, OfP4 has an allocator. It's a pretty simple one. It uses just a first fit algorithm for the moment. So, for example, A here would get mapped into the first place it fits, which is the OVS reg1 register. And then Y and Z at the end might get mapped into reg15 if that's what was left at the end of the allocation process. So we've looked at P4 fields and metadata and how OfP4 maps those to OVS. Now let's look at entire tables. On the left, we've got a sample P4 table definition. The table definition defines two kinds of things: the table key, or what it matches on, and the table actions, or what happens when a packet matches when the packet matches in the table or when it doesn't match anything. OfP4 translates each flow added to the P4 table into an OVS flow. Let's look at the key part first. Each line in this key defines some field or expression that a flow in the table matches and how it matches. OfP4 has to translate each of these matches into part of an OpenFlow match. Let's look at each of them in this example. So the first line defines an exact match on the input port. OfP4 can translate this directly into an OpenFlow match on import. The second line is a bit more complicated. This one says that a flow in this table matches on whether the packet has a VLAN header. OfP4 translates this differently based on the value inserted into the table. If a flow in the table says to match on false, meaning to match a packet without a VLAN header, then OfP4 translates this into an equivalent OpenFlow match. If it says to match on true, for a packet that has a VLAN header, then it translates into a different OpenFlow match. Final line is a P4 optional match, so that whatever inserts a flow into the P4 table can choose whether to match on it or not. If it does match, then OfP4 translates it into a match on the VLAN that the user specified. And if no match was specified, then OfP4 omits that from the OpenFlow match expression entirely. So we've looked at the table keys. Now it's time to look at the actions part of a P4 table. Here's a little more detail on the actions that we saw on the previous slide. Each named action has an implementation elsewhere in the P4 program. The implementations look a lot like functions in a normal language. Each time a user inserts a flow into the P4 table, it specifies the action to use and the parameters to pass in if that action takes any. OfP4 translates the P4 action code into OVS actions. For example, this implementation of a drop action changes the standard metadata to indicate that the packet should be dropped. Then it jumps to the end of the pipeline with exit. OfP4 happened to allocate reg3 to this feature, so it translates it into setting that field. Then it translates exit into jumping to the end of the OfP4 pipeline, which happens to be OpenFlow 31 in this case. The translations of these other actions are also straightforward. Each of them sets a metadata field. The resubmits in these cases are just going to the next table in OfP4's OpenFlow pipeline, since the actions don't do anything to disrupt the control flow. We need to talk about two more aspects of P4 and OpenFlow tables. They're related. One is priorities, and the other is default actions. In OpenFlow, every flow has a priority. In P4, flows in a flow table only have a priority if it would be relevant. If a table only has exact match keys, then there's no need for a priority because it would never come into play. The table we've been using for our example has an optional key field for its VLAN ID, which means that P4 runtime requires us to specify a priority for it whenever we insert a flow. That's true even though any sensible use of this particular table would only need two priorities, a high one for flows that match on the VLAN ID and a low one for flows that ignore it. The other aspect is default actions. A P4 table has to declare a default action. This is the action that gets executed if none of the flows in the table matches a packet that reaches it. OpenFlow has the concept of a default action, but it's a lot simpler, and usually it just means that the packet gets dropped. So OfP4 has to implement the P4 concept of a default action in OpenFlow somehow. It does that with an OpenFlow flow that matches on nothing, which matches every packet with a priority of 0 so that it becomes a fallback. Here's an example. It shows how the drop action gets used as the default action for this table that we've been looking at. Something that surprised me about P4 at first, by the way, is that the default action is configurable. This and changeable at runtime. This table could list multiple default actions, and then the controller could change the one in use at runtime. We can mark the default action as const if that's never going to be useful. Since the default action uses priority 0, any other P4 flow has to use a higher priority. That could be a problem if the P4 controller wanted to use all the 16-bit priority range that OpenFlow supports. P4 doesn't require a switch to support any particular range of priorities though, so OfP4 just limits the range of priorities that it offers the controller by making sure that any non-default OpenFlow flow has priority of at least 1. Now, we've talked about how P4 flow tables get implemented. P4 also has programming control flow constructs like if statements. let's look at how an if statement in P4 can get implemented in OpenFlow. In short, an if statement becomes a flow table of its own. Take the example here. When the expression is true, the packet goes through the learned dest flow table, and when it's false, it gets skipped. The idea is to use the MAC learning table for sending packets only when we don't already know that the packet needs to get flooded to all the ports. So how does OFP4 translate this into a flow table? Let's start by looking at each of the components of the expression. The first term checks whether the program metadata named meta.flood is 0. That might be represented in OpenFlow by bit 12 of reg5. The second term checks whether the multicast bit of the Ethernet destination address is 0. That is represented by bit 40 of dldest, the data link destination in OpenFlow. And finally, let's make the assumption that we're generating table 6 in OpenFlow and that the MAC learning table we want to execute or skip is table 7. Here's an outline of the idea. Table 6 implements our if. If the expression is true, it jumps to table 7, which does whatever it needs to do for MAC learning, and then goes on to table 8 to resume the main execution path. If the expression is false, it jumps to table 8, skipping over the MAC learning table. And then, finally, here's how OFP4 might emit that logic into OpenFlow. It follows the same pattern. The first flow checks the metadata bit and the multicast bit using the kind of awkward syntax that OVS accepts, and jumps to table 7 if there's a match. The second flow has a lower priority and matches anything else and jumps past the MAC learning table to table 8. Let's look at another piece of the puzzle. Near the beginning of the talk, I mentioned that OFP4 has an architecture that puts packet buffering and replication between an ingress and egress pipeline. That's common for P4 implementations, but it's not something that OVS has built in. Let's talk about how to implement that piece. What we do is to stick a table that does all of this functionality in the middle of the OFP4 generated collection of flow tables. It might, for example, end up as table 31. The flows in that flow table are what implement the functionality. At runtime, the compiler determines how replication, or the controller determines how replication works. The controller uses RPC messages to the switch over P4 runtime to assign sets of ports to multicast group IDs. OFP4 then sets up a flow in OVS for each multicast group. When a packet passes from the Egress Pipeline into table 31, if the P4 program assigned the packet to a multicast group, then it hits a flow that matches on the group ID and sends a copy of the packet to the Egress Pipeline for each port in the group. Take group 12. This is an example flow here that shows how OFP4 would implement multicast for ports 1 through 5. The flow matches on the group ID, and the actions clone to port 1 and jump to the egress pipeline, clone to port 2 and jump to the egress pipeline, and so on. The clone action is well designed for this purpose because it saves and restores the packet headers and metadata so that regardless of what the egress pipeline does for one output port, it won't affect behavior for the others. Here's another example for group 23, which follows the same pattern. Finally, a lot of packets won't go to a multicast group at all. For those, OFP4 just jumps to the egress pipeline directly. P4 digests are a way for the switch to send a message to higher level software. They let a P4 program assemble some data into a structure, attach an identifier to it, and then ship it off. The software on the other end, which for a hardware switch is probably running on the host CPU, can then respond to it however it likes. Here's an example of how that might work for MAC learning. Suppose the packet comes in and its source MAC isn't known yet. This code shows how relevant info could be packed up into a structure and sent off to the host CPU. The host CPU would then presumably use it to update the MAC learning tables. OFP4 doesn't support digests yet, but they aren't conceptually complicated. At the OpenFlow flow level, OFP4 implements a digest with an OpenFlow action that sends the packet to the OpenFlow controller with user data that identifies the type of digest. Then, when OVS executes that action, we can think of it in terms of the structure of OFP4, like I showed early in the talk. OVS sends the packet and metadata to OFP4 over OpenFlow, since OFP4 is its OpenFlow controller. Then, OFP4 takes the packet and assembles the digest that the P4 program wants from the packet and the metadata associated with it. It might seem like it needs more information to produce the digest. I think it can do it because the OpenFlow metadata includes all the state of the executing program. OfP4 then, finally, sends the digest to the P4 runtime network controller, and we're done. So we've talked about how OfP4 can implement things, but even with what I think of as the cleverness here, it has a lot of limitations. To start, it's not what I'd call useful yet. It's very much an experiment. I don't expect it to be useful for real work, and maybe not even for many kinds of experiments yet. It's a research project. Don't download it and plan to use it for your P4 project. Beyond that, there's a bunch of stuff that's going to be difficult to implement. One good example is arithmetic. The P4 language allows for mostly arbitrary integer expressions. On the other hand, OVS doesn't support any kind of integer arithmetic. There's no add or subtract, and definitely not multiply or divide. You can compare fields and metadata bits against constants for equality, and that's about it. There are ways to kludge around these limitations, but they're not going to get you very far in practical situations. If OfP4 becomes useful, and this is an important limitation, we can do things about it by adding features to OVS. OfP4 is subject to other OVS limitations. OfP4 likes to use up lots of OpenFlow tables, for example. You only get 256 of these tables, or just 128 if you play by the rules that OVS suggests in the documentation. That's something that OfP4 can work around by using some metadata bits in place of OpenFlow table numbers. But OVS also has relatively limited metadata size. It has about 64 bytes of metadata, which really is not a lot for handling a packet in any sophisticated way. The size could be expanded by modifying OVS, and OfP4 might also be able to allocate it more efficiently. Another limitation is compatibility with existing P4 programs. The P4 programs out there aren't written to handle the P4 architecture that OfP4 exposes, which could make it hard to port them to OfP4. It might be possible over time to improve the compatibility, especially if it turns out to be worthwhile to modify OVS to better suit P4. Finally, so far, there's a lot in the OfP4 implementation that's kind of brittle, meaning that sometimes things don't work, and a surprisingly small change to the P4 program can make it work, or vice versa. I hope that this brittleness is just because we haven't spent too much time working on it and with it yet. So thank you for listening, and here's a link to the repository that has OfP4 in it. It has other things in it, and you'll find the OfP4 implementation in the OfP4 subdirectory. And I can now answer your questions.
Okay, let's take our speaker. I think Ben is online. Ben, can you hear us?
Yeah, I'm here. Can you hear me?
Yes, we can hear you.
Great.
Loud and clear. Okay, let me check if we have any questions in the room. Any questions on the chat?
Nothing on the chat.
Nothing on the chat? Okay. I do have a question. Ben,
Sure.
I think OVS supports a fairly number of packet headers. So I wonder if you, while you were researching this, if you found any use case that could not be translated from P4 to OVS because OVS didn't support the packet header.
Okay. So I didn't, but that's partly because I haven't gone through a large number of P4 programs. I haven't been doing it from the perspective of we've got a bunch of P4 programs we'd like to run. I've been doing it from the perspective of I'm building a larger system that I'd like to use P4 in, and I needed a P4 software implementation. So I'm building new stuff. I'm not mostly trying to make the existing library of P4 programs work.
Okay, yeah, that was just curiosity because while you're researching some use cases, maybe you found something that it's missing in OVS, and it would be nice Most probably just a matter of adding a header to the OVS and having it fix it. But yeah, it was more a curiosity if you found such case.
Yeah, that's a perfectly fair question. And like here's an example of something that wouldn't work directly. There are P4 programs out there that are doing connection tracking, that are taking things like the TCP source port and TCP sequence numbers and acknowledgement numbers, and throwing those into a P4 tables. P4 calls them registers. It means something different from OpenFlow registers. And that's not going to work directly with OVS, because OVS doesn't give you direct access to those. If you were going to port one of those programs to OfP4, then you'd want to use the OVS features for those things instead, where you tell it to use the OVS connection tracker instead of trying to do it by hand in P4.
My next question would be, what is your next steps for this research? Do you plan to continue with this?
I do plan to continue working on it. My goal is to get some simple programs, maybe a very simplified version of OVN working. And our larger goal with NERPA, the project that this came out of, is to be able to build a complete system, management plane, control plane, data plane, in a much more unified way. And we want to do that with P4, and we needed a data plane for it.
Okay. All right, let me check again if there are no other questions in the room.
What do we have to do to get Ben back into in-person conference?
Did you hear it?
That's a fair question. What would it take me to get back to an in-person conference? Well, it's not really. So I'd love to be there. I've just got some family issues that make it difficult for me to travel. If those resolve, maybe they will by next year, then yeah, I'd love to travel and be part of the conference in person.
Awesome. Yeah. We missed some friends this time. Hopefully we can see all the friends in the next OVS conference. With that said, I think this was our last talk, right? We should thank our speaker again.